morning, students. I am N.V. Krishna Rao, Assistant Professor, CSE Department. I am handling the compiler design for the 5th semester. So, now we will discuss the parser, context-free grammars, and derivation in this today's class. So, what is the role of a parser? Right? So, source program will be input to the lexical analyzer. The lexical analyzer will give a list of tokens. Right? The lexical analyzer will take the source program and gives a sequence of tokens. The sequence of tokens will be the input to the syntax analyzer. The sequence of the tokens will be the input to the syntax analyzer. This syntax analyzer will request the next sequence of the tokens. Right? This symbol table will be interact with the lexical analyzer and also the syntax analyzer, and the syntax analyzer will request next token and get the tokens, and it will perform it gives the output a parse tree. The parse tree will be the input to the semantic analyzer. So the main task of the syntax analyzer, it will take the input, the sequence of token, and it will follow the syntax rules of the programming language. The syntax rules of the programming language are represented with the context-free grammars. Right? The context-free grammars, the recursive context-free grammars are represented the syntax rules of the programming language. Right? So here, this syntax analyzer will follow the syntax rules represented by the context-free grammars, and it will group the sequence of the tokens, and it will give a parse tree as a output. It will read a sequence of tokens, and it follows the syntax analyzer. The parser program will consist the context-free grammar productions rules represented by the context-free grammar productions, right, which resemble the syntax of the programming language, and grouping of these tokens and will result to parse tree. So the output of the syntax analyzer is parse trees. Right? The output of the syntax analyzer is parse trees. So the syntax analyzer is the compiler program, is the second phase of the compiler, which consists of all the syntax rules of the programming language in the form of context-free productions. Language productions. So this syntax analyzer main task, it follows its rules and regulations of the productions, context-free grammar productions, and it groups all the tokens, sequence of the tokens into a parse trees. Right? So the parse trees is the output of the syntax analyzer phase, and it will given to input to the semantic analyzer. Right? So here it takes the strings of tokens from the lexical analyzer and verifies the structure generated by the tokens based on the grammar of the source language. Right? So it builds the parse trees. If it found any errors, it will generate the error message. For example, C language, if we consider, all the statements must end with a semicolon. If it is unable to find the semicolon, simply it will generate the error message. Right? It will generate the LMSs. So all such syntactic errors will be generated by the parser. For example, if you are declaring the multiple identifiers, multiple variables, it must be separated by commas. If any comma is missing, that is reported by this parsers, right? So error recovery for commonly occurring errors so that we can continue processing its input. So that error recovery, error handler is a procedure in the compiler construction. So it will handle all these error messages. If it is a regular error message, it will be handled by error handler itself. Otherwise, it will generate the error messages, right? So that is the role of a parser, right? We represent the parser in terms of the context-free grammar production. Now we will refer what is a context-free grammar and how we can represent the syntactic rules. So here we represent the context-free grammars in the form of a quadruple: variables, terminals, productions, and start symbol, VTPS. So here VTPS we use here variables, terminals, productions, and start symbol, right? VTPS. Here the first one, variables. V is finite set of non-terminal symbols are the variables, right? Then T is a finite set of terminals where V intersection T equal to null, right? P is a finite set of rules for the productions, right? V means a set of variables are non-terminals. T means a set of terminals. The intersection of variables and terminals should be null. Then P is a set of productions. We represent the productions in the form of a variable giving a closure of variables union terminals, right? A productions P, the productions we represented as a variables giving variables union terminal closure. What is the meaning of closure? Occurrence of zero or more number of variables or terminals, right? Then here S will represent the star symbol of the represent the language being defined, right? S is a start symbol. V is variables, T is the terminals, P is the productions, S is the start symbol, right? Each variable represent a set of strings, right? What is the terminal? The symbol that forms the strings of the language being defined, right? So every variable represent some set of strings, but the strings are represented with the a terminal symbols. A string is a group of terminal symbols, right? So here these productions might be recursive definitions. It represents the recursive definition of the language. It might be a simple productions or it might be recursive definitions. Other variables represent auxiliary classes of the strings, right? That are used to help define the language of the start symbol, right? For every grammar, there will be a start symbol with representing the starting of the language, right? It will be connected to other variables of the grammar. Each production is in the form of head gives body, where head is a variable and body is a string of zero or more number of terminals and variables, right? Each production is in the form of head gives body. Head gives body, where head is a variable and body is a string of 0 or more terminals and variables. Right? So here G equal to S is a variable, AB are the terminals, P is the protection, S is a starting variable. We are defining the protections as S is a starting variable, AB is terminals, right? P is a list of protections, S is a starting variable. We are representing a first example grammar protection as VTPS, right? The variables we have only one. That variable is S only. Only one variable. We have two terminals, A comma B. P will represent a list of protections and S will represent starting variable. So the protections, one is S gives ASA, S gives BSB, right? S gives ASA, S gives BSB and S gives epsilon. So we have three protections. S gives ASA, S gives BSB, S gives epsilon, right? So here the first protection ASA, second protection BSB, third protection S gives epsilon. We can write the three in this a simple form. S gives ASA BSB slash epsilon, right? Here we can write in multiple or we can write a simple one, right? So here S gives ASA, BSB or epsilon. We are combining all the three protection into this form. So here this is a second example. We are representing the grammar in the form of G equal to V T P S, where the V is S and F variables, terminals are 0 and 1, S is the starting variable, and the list of protections are S gives 00S slash 11F. So S has two protections, 00S and 11F, that we are combined it into in this single common simple form, right? Then F equal to 00F slash epsilon. Here P has 11F, so S and F are related. Then the protections are considered, right? All the variables which are in the grammar should connect with our starting variable. Otherwise, we say that variable is useless variable and we remove the protections, right? So this is a compact form. Then derivations. The protections of a grammar are used to derive the string, right? For any string should be derived from the protections of the grammar. Then we say the string is accepted by the grammar, right? If the string is derived by the protections of the grammar, then we say the string is accepted. The string is accepted by the particular grammar, right? So one-step derivation are direct derivations. So here V is one-step derivation from U, written as U implies V. So V is derived directly from U, right? So U equal to X alpha Z. V equal to X beta Z. If alpha gives beta is a protection in P, then we are alpha is replaced by beta, then the U implies the V. So the V sentence is derived to V sentence by using the production alpha gives beta in the grammar, right? So we can say that X alpha Z derives X beta Z or X alpha Z yields to X beta Z. Here, if it is a simple example we are considering, A gives AA slash B and B gives BB slash epsilon, right? So here a simple sample derivation. S is a starting variable. Always the derivation of a string start with a starting symbol. Always the derivation of a string should start with the from starting variable S. If S gives A, so from the production number 1, we are deriving as A gives A, right? Then we are using the same production 1 and we are replacing A as A, capital A, 2S. And we apply the same once again. So 3S, capital A, 3Bs. Then we are applying the B, right? We are replacing the B with A with B. Then we are replacing that B with small b and capital B, right? We are replacing small capital B, the variable B with the capital B is replacing with the small b and capital B. Applying the production number 3. Once again we apply the same production number 3. So once again we are applying B and capital B. Then we replace capital B with the epsilon, right? So then we replace capital B as which generate the epsilon, so that the final resultant string consists only the terminal symbols. What are the terminal symbols? 3A's followed by 2B's followed by 3A's, right? So this is a simple derivation. Always the derivations should start from the starting variable, and we apply a list of productions one by one such that finally it results a sequence of the terminals of the given string. It must derive the terminals of the given string. Then the string is accepted by the grammar, and also it is a derivation, right? It is also called as a derivation of the given string. So here, if you derives V in multiple steps, then we use star, right? So U1, U2 gives UK2, V, right? Here we are considering the same example. We are considering the same string, right? First production we are applying A gives A. Then we are applying the same first production once again. It is giving A, capital A, and 3S, variable A, 3S by applying the first production. Then we are applying the second production, right? Here capital A giving capital B. Then we are applying the third production. Then we are applying the third production, and finally we are applying the fourth production. So variable B giving epsilon such that gives a sequence of the terminals only which matches with our given string. Here our starting variable A is deriving a sequence of symbols, our given string, in multiple steps. So that we represent A will derive the V in star, represent with the star, right? So A represent, A gives star derivation, right? Gives the 3S, 2B's and 3S, right? Here directly single step, key step derivation, and derivations of 0 or more steps, right? single step derivation, k-step derivations, and derivations of 0 or more steps. Right? Here, if G is a VTPS, is a context free gamma, then the language specified by G or the language of G is a context free language denoted by L of G. G is a grammar, VTPS we represented. The language that is accepted by context, this grammar we call as context free language. The context free language we represented as L of G. Right? Context free language we represent as L of G. Here, this L of G is a context free language which consists of all the strings W. W is a string. It consists the all the strings which belongs to star closure of the terminal symbols. Right? A string is always a sequence of terminals only. So the W belongs to star closure of terminals. Right? This W must be derived from the starting symbol. So S must derive star derivation, right, gives the W, right. The set of strings over T derivable from start symbol S. Then the it belongs to L of G are called a sentence, right. Here, these are the one more example. G is variable S, terminal 01, and P is the protections. S gives 0S1 slash epsilon, and the starting symbol is S. Then the language accepted by this grammar we can represent as 0 power n, 1 power n, slash n greater than or equal to 0. So here L of G is a grammar, a language that is accepted by the given grammar. What is the strings it will consist? It consists of all the sequence of zeros followed by ones, right? All the sequence of zeros followed by ones, right? 0 power n followed by 1 power n. Okay. Now, balanced parentheses. This is another example for the balanced parentheses. So the P we represent as simply epsilon. Parenthesis P. The P in the second production will represent recursion. And third one will represent as simply P and P for the recursive purpose. It might be a simple parenthesis or flower brackets. In the next example, we have represent P as with a flower brackets, right? So this is the example for the context free grammars. Then representation of the derivation of a given string in the tree form called as the derivation tree or parse tree, right? The sequence of substitutions used to obtain the string using the context free grammar is called a derivation and may be represented by a tree called as derivation tree or parse tree, right? So here parse tree or derivation tree means that representing the derivation of the any given string in the tree structure is derivation tree or parse tree. Here this will result the tree will result, it will shows the substitutions of the sequence of the substitutions used in the derivation of the given string. So a derivation tree or parse tree is an ordered rooted tree that graphically represents the semantic information of a string derived from the context free grammar, right? So using the protections of the context free grammar will replace one step to another step. All that derivative steps will be represented in the tree form the tree form called as derivation tree or parse tree. Right? Here, the first one A, the root. The root we are replaced by first production A. Once again, we replace it by first production. Right? Then once again, we replace with the first productions. So 3S, capital A, 3S. Then we replaced by the second production. In the previous derivation example, we replace A with the second production B. Then B is replaced with our third production, small b, capital B. Once again, we are using the third production, right? Small b, capital B. Then finally, we are playing the fourth production, B gives null string. So here, which represent 3A's, 2B's followed by 3A's, right? 3A's, 2B's and 3A's, right? Here, the root label is start node. Each integer label is variable, right? The capital A's, capital B's are the integer labels which are all variables, right? The root label is start node, that is starting variable. Always the starting variable we represent the grammar VTPS, right? S is a starting variable. So that root always will be the start node, right? So each parent and child relation is a derivation step. Each parent-child relation is a derivation step. So all the derivation steps we are represented with the form of parent-child relation, right? So each leaf label is a terminal or epsilon. Each leaf label is always a terminal or epsilon, right? The leaves of a parse tree, when read left to right, are called the frontier or yield of the tree, right? We group the leaves from the left to right of the parse tree is the given string, is the derived string, simply we call as frontier or yield of the tree, right? Sentential form or partial derivation tree. A partial derivation tree is a subtree of a parse tree such that either all its children are the subtree or none of them are in the subtree, right? A partial derivation tree is a subtree, right, of a parse tree such that either all its children are in the subtree or none of them are in the subtree. Okay. So here is an example. S gives ASB slash epsilon. So here we are deriving the sentence 3A's followed by 3B's. By applying deriving the S equal to ASB, then applying the same production one second time, 2A's S 2B's, applying the same production third time, 3A's S 3B's will result the sentence 3A's 3B's. The derivation or yield of the tree. The derivation yield of a parse tree is a final string obtained by concatenating the labels of the leaves of the tree from left to right, ignoring the nulls. However, if all the leaves are null, the derivation is null. So, the yield of a tree is nothing but a grouping of all the leaves from the left to right. Then, we'll see the one more example here, right? What is the grammar that is given? S gives to S slash ASB slash epsilon. That is the grammar productions is given, right? Now, what is the string we want to derive? W equal to AB, 2A's and 2B's. That is a string we want to derive. Now, first one we are selecting the production number 1. So, in the production number 1, S gives double S. Then, The first S is replaced with the second production ASB, right? Then we are using the third production, S gives null, so resulting to ABS. Then we are applying, just now till now we applied first production, then we applied the second production, then we applied the third production, right? Now apply the once again second production, which gives ABASB. Then S gives ASB. Apply the second production only. Then apply the third production. Apply the third production. S gives epsilon. What is it finally gives? AB, 2 A's and 2 B's. So what is the sequence of order? First production we applied. Then second production is applied. Then third production is applied. So we got the ABS. Then we applied the second production. Once again we applied the second production. Then we applied the third production in deriving our final string that we are representing in the derivation form. So S gives 2S, S gives ASB, that S gives epsilon. Then second S gives ASB, once again S giving ASB, second production, then applying the third production. So now in this class we have discussed what is a parser, what is the task of the parser, and context-free grammars and derivations of a grammar of a given string, derivation of a given string, and derivation tree. So I'm closing this class for today. We will continue the remaining topics in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.